The third and ultimate step forward then was left up to this fellow. His name is Schrödinger. Okay? Austrian, as I recall. I believe it was Austrian. He applied three-dimensional wave mathematics, in other words, differential equations in 3 dimensions, to the electron in the hydrogen atom. And he was able to get a solution. It's not actually that hard. And the characteristics of the solution absolutely astounded everybody who saw them. He said the electron, by doing that and applying certain sort of realistic ideas, that the electron has to be, it has to have a probability of 1 of being somewhere in the atom, and it has to be, its wave has to be continuous and things like that. What he got was the electron in the hydrogen atom could occupy only certain fixed energy levels. And this was completely analogous to the fundamental, the first overtone, the second overtone, third overtone, but the actual energies were the exact same things, the same energies to as many significant figures as you want to pursue as Bohr had. So, the same result from 2 completely different approaches. When that happens in science, the first conclusion you should make is that that result probably is the truth, at least until something better comes along. And that's what happened here. The energy diagram is the same one I showed you before. But in addition to Bohr's orbital energies, if you will, which Schrödinger called shells, there were other structural aspects of the hydrogen atom that Bohr didn't think about, had no way to get to. And the fine structure of the hydrogen atom, according to Erwin Schrödinger, was that there were shells, and within the shells there were subshells, and within the subshells there were the ultimate state where the electron could be, orbitals. And these things were named orbitals, I gather, in deference to Bohr's orbits, but they're not at all like orbits, like Bohr's orbits. The only place where they are similar to one another is they all have the same energy. Each one has the same energy in its Bohr counterpart. Now, this three-dimensional equation that Schrödinger solved produced an infinite number of solutions. It produced a solution of the lowest possible energy, which matched Bohr's n is equal to 1 shell, orbit, energy level, if you will. And each one of these things described what was called an atomic orbital. Each description, mathematic description, was given the symbol Greek psi. And psi is a mathematical function that fixes the energy states the electrons can occupy. Each orbital, remember, psi doesn't, psi describes the orbital, not the electron. The electron can occupy the state created and described by psi, right? Now, if you square the wave function for a particular orbital and integrate over a particular area, x, y, z, you produce the probability of finding the electron in that region of space. We're not going to go there, but it was as de Broglie ultimately, I think, thought it would be, and that Heisenberg completely agreed with, that if you wanted the energy, each one of these orbitals have a specific energy. If you know that, you have to give up knowing for sure at any given point where the electron can be. Well, this was one of the most amazing series of things that's ever happened in science. Niels Bohr got the Nobel Prize in 1922. Louis de Broglie got it in 29. Heisenberg got it in 32. And Schrödinger got it in 33. there has never been a series of scientific advancements that matched what these fellows did. Now, I want to talk about the quality and the characteristics of Schrödinger's states of the hydrogen atom. Remember, this just was hydrogen atom. In order to describe the ground state, for example, what is sometimes done is to use a scatter diagram. We can't tell at any given instant where the electron is, but imagine that you were able to have a camera which could see an electron and could take a series of pictures over a period of time, kind of a time-lapse thing, or a, what do they call it, where you keep the lens open and you collect a whole series of, I can't think of the name of it, but anyhow, this is what you would get for the ground state of the hydrogen atom using its wave function. What's its wave function? Ooh, that sounds scary, doesn't it? What is it? It's not scary at all. The wave function for the ground state, I'll tell you more about this 1s later, is equal to a constant times e to the minus r multiplied by another constant. Well, heavens, that's just a negative exponential. Anybody in here could deal with that, plug it into their calculator. That's what the ground state came out to be. And it gave, for example, there's no angle dependence here. So it says that ground state, whatever it is, it's spherical. Okay? And, of course, we don't know at any given time where the electron is, but it's along, the distance from the nucleus to the electron is plotted against this radial line here, the distance to which would be r, and that's the r that's down here. Okay? Now, in order to get more insight into this, something called the radial density distribution was invented. This is just a little mathematical tool, and what it's supposed to do, this tool, is to allow you to imagine you have an electron density meter, and you're standing at the nucleus of a hydrogen atom, and you take a reading, and then you take a few microsteps along the radius r here. You take another reading, and you do this until you're tired of doing it. You take all the data home, and you make a plot. The plot looks like this. This is psi squared, actually modified a little bit to take into account the characteristics of a sphere, plotted against the value of r. And it shows that the probability of finding an electron here is almost zero at the nucleus, and it goes up sharply, and it goes through a maximum, and it comes down, and then it approaches the horizontal axis asymptotically. Okay? And this is a plot of the electron density versus radial distance. Now, here's something that's very cool about that plot. The maximum occurs at 0.529 angstroms. That's where it occurs. And that was the radius of the first Bohr orbit. Again, you have the same concept arrived at from two different directions. Quantum mechanics said the most probable distance to find an electron in this state, in the hydrogen atom, is 0.529 angstroms. Bohr said if the electron's in the ground state, it's exactly 0.529 angstroms. Okay? We know that if Heisenberg, if the Heisenberg uncertainty principle is true, Bohr couldn't say what I just said that he did, but this description of the probability is completely acceptable.
Question?
Yes?
Would the area under the curve be 1 then?
He asked if the area under the curve would be 1. And to answer that, let me tell you that each wave function is normalized so that the total probability of finding the electron in that state is 1. So the area under the curve should be 1. Should be 1. Thank you for your question. That was a good one. Okay. Now, the fine structure of the hydrogen atom is something we need to know about. And it all came from Schrödinger's solution to his three-dimensional function. Instead of having one quantum number like Bohr had, quantum mechanics came out with three quantum numbers that were related to one another in a fairly straightforward way. The three quantum numbers, the first one was given the symbol n, and it was called the principal quantum number, the same way Bohr did. It has the same kind of whole number values, not including 0, that Bohr indicated that it should, but now this was not an arbitrary choice. You could see clearly from the mathematics what values n could have, and it turned out they were exactly the same as Bohr assumed that they would have. Just scary parallels between these things. The second one, the second quantum number, is called the orbital angular momentum quantum number, or sometimes just the angular momentum quantum number, L. And the third one is m sub L, and that's called the magnetic quantum number. Now, the relationship between these is something you need to be absolutely familiar with, because these things are going to dictate a lot that comes later, approaching and including electron configuration, which fixes everything that comes later in this course. The principal quantum number is a positive integer not including 0. It specifies what Bohr called the energy level and what Schrödinger called the shell of the hydrogen atom. And it also specifies the size of the orbitals within that shell. The angular momentum quantum number L is an integer that goes from 0 up to n minus 1. So L can have a value of 0, n cannot. And the largest value that L can have in a particular shell, specified by n, is n minus 1. L dictates the type of subshell that we are talking about, and the subshells differ in the shape of the orbitals that make them up. So L dictates both of these things, which subshell we're talking about, and the shape of the orbitals within it. If, for example, in a shell with n is equal to 2, if we apply this idea, L could have values of 0 or 1. It can't have 2 because the maximum value it can have is n minus 1, and if n is 2, 0 and 1 are the only allowed values. Cannot be negative. Neither can n. Okay? If n were 3, if we were talking about shell number 3 in the hydrogen atom, L could then be 0, 1, or 2. Okay? And for each value of L, we have dictated or specified a subshell. So when n was 2, L could have 2 values. That makes 2 subshells. When n was 3, L could have 3 values, and that means 3 subshells. So the number of different L values is equal to the value of n. Is everybody comfortable with this so far? We're just going to take this and we're going to build up all 3 of them, show you how they're related to one another, and strongly urge you to learn the relationship. Okay. The magnetic quantum number, m sub L, is also an integer, but now it can have values from negative L through 0 up to positive L. The smallest value it can have is negative L, assuming the number line, and the largest value it can have is positive L, and it can have integer values or whole number values all the way in between. Now, m sub L does something different. It prescribes the physical orientation of an orbital around the Cartesian coordinates, z-axis, x-axis, y-axis. The orbitals within a particular type of subshell, for example, that you know about, the p, lie along the z-axis, along the x-axis, along the y-axis. That is specified by the value of m sub L that they have. And this is done through the wave function, which describes that particular structure within the atom, which is an orbital. So when L is equal to 0, m sub L can only be 0. But when L is equal to 1, m sub L can be -1, 0, or +1. A tip: the number of possible m sub L values or orbitals for a given L value, given subshell, is 2L plus 1. 2L plus 1. If you need to count how many m sub L values, which is how many orbitals we have in a given subshell, it's 2 times L plus 1 for that subshell. Okay, so here's just a little diagram that shows you the relationships we have so far here between these three quantum numbers. If n takes values of 1, 2, and 3, in each case we can see what the possible L values are. The second line here is L values. If n is equal to 1, L can only be 0. Okay? If n is equal to 2, L can be 0 and 1. These are 2 subshells. Here's 1 subshell. If n is equal to 3, not surprisingly, L can be 0, 1, or 2, so there's 3 subshells. Down here is m sub L, and m sub L, if L is 0, m sub L has to be 0. And that's the same thing over here. For n is equal to 2 and L is equal to 0, m sub L can only be equal to 0. So for that subshell, this is a subshell here, these are shells up here, and these are the subshells right here. Okay, so for that subshell, there's only 1 orbital. But when L is equal to 1, we just said m sub L could take 3 values, -1, 0, and +1. Each one of those corresponds to an orbital. You could think of this sort of like the address of an electron. N is sort of like the state, and L is sort of like the city, and m sub L is sort of like the street. You know, I know that's simple, too simple-minded, but that's what it boils down to, sort of. So we get a number of orbitals in each subshell that's dictated by the value of L, 2L plus 1. Okay, determining the quantum numbers for an energy level. Let's look at this problem and these questions. What values of L and m sub L quantum numbers are allowed for the n is equal to 3 shell? Don't look back at your notes. Okay, what values of L and m sub L quantum numbers are allowed for the n is equal to 3 shell? And B, how many orbitals are present in the n is equal to 3 shell? So, if we look at the value of n is equal to 3 here, we have the possibilities for L going from 0 up to 2. 0, 1, and 2. For n is equal to 3, L can be 0, 1, and 2, right? So those, if you look at these L values, are in every case representative of the shell, of the subshells. So for the n is equal to 3 shell, L says you have 3 subshells. They're 0, 1, and 2. But it asks us for the m sub L values too, and they are dictated by the values of L. So we determine m sub L from each L. For L is equal to 0, the first one here, we have m sub L is equal to 0. That's the only thing it can be. For the second one, L is equal to 1, m sub L runs from -1 up to +1 in whole number steps. So this is +1, 0, and -1 in whatever order you want to write them down. Okay? For L is equal to 2, which is the largest value L can have, m sub L has 2L plus 1. 2 times 2 plus 1 is 5. 5 values, +2, +1, 0, -1, -2, or in the reverse order, if you please. Okay? Now, the relationship between the quantum numbers is what lets us do this. And you should have clear in your mind now that for the value of n, that tells us what shell we are discussing. Then once we know that number, we know what possible subshells there are, as we see here. And once we know the subshell values according to their L, we can determine the M sub L values from it. So there are 9 M sub L values. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means there are 9 orbitals. And each orbital, and I want you to be sure to take this with you from this slide, each orbital is specified by a value of N, a value of L, and a value of M sub L. Okay, and we had gone through this example. What values of L and M sub L quantum numbers are allowed for the n is equal to 3 shell? How many orbitals are present in the n is equal to 3 shell? And I didn't finish the last line of this according to the recording, so let me go back through it. If n is equal to 3, L can only take values from 0 up to n minus 1. So that would be L, the possible values of L are 0, 1, and 2. L determines what M sub L can be. M sub L can take values from negative L up to positive L. So for L is equal to 0, M sub L can only be 0. For L is equal to 1, M sub L can be plus 1, 0, minus 1. And for L is equal to 2, this value, M sub L can be plus 2, plus 1, 0, minus 1, minus 2. Now, those are, each one of those corresponds to an allowed set of the 3 quantum numbers. We start with n is equal to 3, and then L is equal to 0, and M sub L is equal to 0. 3, 0, 0 is one set, allowed set of quantum numbers for the third shell, and that corresponds to one orbital. So each one of these N, L, and M sub L combinations corresponds to an orbital, and as you can see, there are 9 M sub L values, so there must be 9 orbitals, and I forgot to give you the hint, or the tip. The total number of orbitals in a given shell here is n squared. In this case, 3 squared is 9. So if you want a quick way to calculate the number of orbitals to check yourself or to answer a question, n squared will do it. Number of orbitals in a shell. Questions on that? Okay, good. Subshells are designated by allowed combinations of N and L. Each subshell is labeled with a letter. And you need to learn these letters. They're pretty simple. When L is equal to 0, this corresponds to an S subshell. When L is equal to 1, we call it a P subshell. 2, we call it a D subshell. 3, we call it an F subshell. And if you get any above 3, they go alphabetically from there on, G, H, I, J, K, and so forth. Okay. The subshell, then with N is equal to 2 and L is equal to 0, that's an allowed combination. That would be called 2S. 2 is the value of N, and S indicates L is equal to 0. Likewise, we can say that the 2s orbital, which makes up the 2s subshell, then has quantum number values of 2 for N, 0 for L, and 0 for M sub L. If we go back to the subshell with N is equal to 3 and L is equal to 1, that would be the 3p subshell. L is equal to 1 indicates P. And you do need to learn these. It will have 3 orbitals corresponding to N is equal to 3, L is equal to 1, and M sub L with these 3 values, plus 1, 0, and minus 1. Too fast?
No, it's not on the last slide. Because L is n minus 1, correct?
No. L takes values from 0 up to N minus 1.
0 up to
Yeah, in integer steps. Okay. We have a problem here. Give the name, the magnetic quantum number, and the number of orbitals for each subshell shown below. And we have 1, 2, 3, 4 subshells specified by allowed values of n and l. Okay? So we look at the value of n and the value of l. That tells us what subshell we're talking about. For example, when n is equal to 3 and l is equal to 2, we have the 3D subshell. L is equal to 2 means D. And for n is equal to 3, we would be talking about the 3D. So the possible m sub l values, if l is equal to 2, are negative 1, negative 2, negative 1, 0, positive 1, positive 2, 5, pardon me, 5 values and 5 orbitals. Okay, question about that? Okay, then let's look at the next one. N is equal to 2 and L is equal to 0. If L is equal to 0, it's an S subshell. In this case, it would be the 2S subshell. And the possible M sub L values, since L is equal to 0, there would only be one, and that would be M sub L is equal to 0. And therefore, there would only be one orbital that for N is equal to 2, L is equal to 0, and M sub L is equal to 0. And that's only one. For C, we have N is equal to 5 and L is equal to 1. And L is equal to 1 corresponds to what kind of orbital, what kind of subshell? A P-type subshell. So this would be the 5P. And all P subshells have L is equal to 1. So all P subshells have 3 M sub L values shown here. And all P subshells have 3 orbitals. Okay? Now, D is N is equal to 4 and L is equal to 3. When L is equal to 3, what kind of subshell is that? That's an F subshell. So it would be N is equal to 4, so it would be the 4F. And M sub L values would start with negative 3 and go all the way up to positive 3. That's 7 values, so there'll be 7 orbitals in an F subshell. In practice, we won't do G and H and so forth. F is the as far as chemical significance goes at this point. Questions on the answers to this problem? All right, good. The last thing I need to talk about is the shape of atomic orbitals. Now this is a little bit tricky because, you remember Werner Heisenberg, he said, all right, if you're going to use this wave model to describe the electron, and you insist on knowing its energy, then I insist that you're not going to know where it is at any given time. And because of that, and you can understand this, if you were going to measure the energy of that electron by some sort of a probe, you would disturb the electron in the process. So wherever it was before you determined its energy, it's not going to be there afterwards. So you have, if you know the energy, you give up knowing where it is. So that's why we talk about electron densities. And the shapes of orbitals boils down to their electron density distributions in 3 dimensions. And all orbitals where L is equal to 0, we call S orbitals. They're all spherical. There's more to them than just a simple sphere. This happens to be a scatter picture of a 2s orbital. I'll have more to say about that in a moment. But you can see it clearly appears to be spherical. And if you turn it, if you spin it, you could see that there appears to be 2 parts of it. There is a spherical shell in the middle that separates this place from that place. And I have another representation of a 2s orbital right here. This is a grapefruit section or an orange section of the 2s atomic orbital. And it is cut this way to show you what the insides of it look like. And we notice, according to the radial density diagrams here, there is a place of high electron density in here, and another place of high electron density out here, and in between these two, there is a node. There is that spherical shell that we saw up here, where the electron density goes to 0. And in the distribution, or in the density probability diagram here, this white-looking segment, I guess segment's the right word, the white-looking segment here corresponds to where the electron density goes to 0, and on the distribution diagram, it's that spot right there. Okay? Now, this is a characteristic of s orbitals, so that the 1s orbital has none of these nodes, as you can see by the distribution. The 2s has 1, the 3s has 2, and that's the pattern for it. If we look at the segment, the orange segment diagram for a 3s here, you can see there are, in fact, 2 nodes, and those nodes correspond to the diagram around 0.5 and around 4 times 10 to the minus 10 meters. Pardon me. So, spherical overall, but having concentric spheres starting with the 2s and going up with the 3s, and a little bit of internal structure there. Questions on s orbital? Okay, p orbitals, where L is equal to 1, have 2 regions of high probability where we'd find the electron, or high electron density. They lie on either side of the nucleus. This is a mathematically accurate representation of 3 dimensions and 2 of a PZ orbital. What is usually used is a simplified diagram that looks more like kind of a dumbbell sort of thing for p orbitals, and this is what that looks like. The nucleus lies on a nodal plane, meaning a node, a plane which is a node in the electron density. No electrons can be there. The electron density for this planar node, and I'll show you this. Here it is, a side view of the 2pz orbital. This nodal plane, electrons cannot be in there. The probability of finding them there is 0. Now, only shells with n is greater than or equal to 2 will have p orbitals. The n is equal to 1 shell doesn't have any. And finally, the energies in polyelectron atoms, which are really part of Chapter 8, but the energy of these things varies such that the most stable one has the lowest value of n. So 2p has a more negative energy than 3p, and that has a more negative energy than 4p. Okay. So strictly speaking, in terms of positive values, 4p is more positive than 3p, is more positive than 2p, etc. So those are the p orbitals. If you take 3 of these together, you get something that looks like this. The pz, the py, and the px follow the respective Cartesian coordinate axes, as you can see here. The 2p subshell consists of the 3 orbitals for which m sub L is equal to +1, 0, and -1. You don't have to know which orbital corresponds to which value of m sub L. Some things we could say about 2p orbitals. They are equivalent within one subshell. They're equivalent in size. They have the same shape, and they have the same energy if you're all in one subshell. The n is equal to 2, L is equal to 1, p subshell has these 3 orbitals. They all look the same. They differ only in their orientation. Okay? Now, the last type of orbitals that we're going to be concerned about are the most complicated ones, and they are the d orbitals. The d orbitals are those for which L is equal to 2, and there are 5 of them because there are 5 m sub L values when L is equal to 2. Plus 2, plus 1, 0, minus 1, minus 2. Each one of those corresponds to a d orbital. Here is an accurate representation of one of the d orbitals. They're given symbols here to indicate something about how they're oriented. The dyz is in the yz plane, and that's about what it would look like if you could see it. The simplified shape is also in the yz plane, but they use skinnier lobes so that it's easier to represent them. It's easier on the technical artist, I guess. Okay. So that's the yz. There's an xz in which we have the lobes, the 4 lobes now. P orbital was 2 lobes like a dumbbell. D orbital is 4 lobes like a cloverleaf. These 4 lobes would all be in the xz plane, as you can see. The third one, like this, is the 3dxy. Its lobes are all in the xy plane, and like its cousins here, the lobes lie between the coordinate axes, not on them. So for dxz, dyz, and dxy, the lobes are in the indicated planes, but they are between, they point between the Cartesian coordinate axes. Okay, so that's 3. The fourth one is called x squared minus y squared, and it's like the xy, but it's rotated 45 degrees so that the lobes are on the coordinate axes for the dx squared minus y squared. You're not going to have to draw these, but you will have to recognize them. So you might be given a picture of several different orbitals and say which one of these is the dxy and which one of them is the dx squared minus y squared. So you could see the difference between them. So that's 4. I said there were 5. The last one is a combination orbital, and it's called the dz squared, and it looks funny. It looks like sort of like a p orbital that ate a very large donut. And this torus of electron density is in the xy plane, and the 2 lobes that go with it, all this is part of one orbital, they are along the z-axis. So learn to recognize each of the 5 d orbitals so that you can pick them out in the lineup if you need to. Here they are with their symbols. Now d orbitals only are found in n is equal to 3 shell and up. There's no 2d or 1d orbitals. It starts with 3d and goes on up from there. And the size, as we said before, for p orbitals, 3d is the smallest, then they get larger as n increases. And here is a workshop. Which of the following orbitals, which are side views, is or are present in a subshell for which n is equal to 3 and L is equal to 2? Well, n is equal to 3 and L is equal to 2. What kind of subshell is this? What kind? S, P, D, F, G, H? It's D. It's a D subshell. So we're looking for d orbitals, something that could be one of the 5 shapes that we just saw. Question? Okay. You may not find this in your slides. I'm not sure. I guess some of you have it. Okay. So we look at this one. It has only 2 lobes. And it's not a dz squared because the torus is missing here. So this is no good. We look at this one from the side. This does look like a dz squared because it has the 2 lobes across from one another. It sort of looks like a big p orbital. And then looking at it at the side, here's the torus in the xy plane. So this one looks good. This one clearly is not a d orbital. It's some kind of an s orbital. It looks like a 2s to me. So take that one out. Now let's look at this one here. 1, 2, 3, 4, 5, 6 lobes. Could it be a d orbital? No. No, this is actually an f orbital. And you don't have to recognize this as an f orbital. You just have to recognize that it's not a d orbital. Finally, here is the last one. We have 4 lobes. Sort of looks like a clover leaf. We can't see what the Cartesian coordinates are, but in terms of the shape, could this be a d orbital? Yes or no? Yeah, it could be. So this is a good one. This could be something like the dxz or the dyz pretty easily. So out of these, the 2 check marks represent the ones that could be present in a subshell for which n is equal to 3 and L is equal to 2. Questions? Okay. Now the last thing that needs to be covered here is energy, but I have a little quantum number quick check before we go ahead. Identifying incorrect quantum numbers. What is wrong with each of the following quantum number designations and or subshell names? So we have n, L, m sub L value, and the name is over here. So n is equal to 1, L is equal to 1, m sub L is equal to 0, and we're naming it the 1p. Is there anything wrong with that? Okay. N, he says, L can only be 0 because n is equal to 1, right? L cannot be equal to n, only n minus 1. So that would mean that this 1p thing over here is no good because L cannot be 1. So there can only be an s orbital in the n is equal to 1 shell. Okay, what about this one? 4, 3 plus 1, it's the 4d. N is equal to 4, that looks okay. M sub L is equal to plus 1, that's in the range of L. Is there anything wrong with this? What is it? He said it's F. L is equal to 3 doesn't correspond to a D subshell. It corresponds to an F subshell. So what's wrong with this is this 4D ought to be a 4F. Questions on that one? Let's see, got one more? Yeah, here's one more. 3, 1, negative 2, the 3p orbitals. N is equal to 3, that looks good. L is equal to 1, that's certainly a p subshell. Is there anything wrong with this? Say it louder. M sub L cannot be equal to negative 2. You're right, because M sub L takes values from L down to minus L. So minus 2 is outside of that. So all of these are bad. Questions on them? If M sub L were a value, a allowed value in that range, then 3p would be okay. I'm sorry, I couldn't hear you. Well, you can cross out the 3p if you want to, but what's really at fault here is that M sub L can't have this value. If you gave M sub L an allowed value, the 3p would be okay. Other questions? Okay. Yes, go ahead.
Then, what would be the values for M sub L?
They go from negative L to positive L. Okay, minus 1, 0, plus 1. Okay, the last thing in Chapter 7 has to do with the energy levels of the hydrogen atom as calculated by Schrödinger, not by Bohr. Okay, the results from Schrödinger look a whole lot like Bohr's results. Here is the energy diagram for the shells in the hydrogen atom. Here they are, each one of them. N is equal to 1 is the ground state. N is equal to 2 is the first excited state. N is equal to 3 is the second. n is equal to 4 is the third excited state. And here are all the subshells, and they have all the same energy according to quantum mechanics. Well, that's exactly what we found from Bohr's model. Notice that these things are getting closer and closer together as n gets larger because of this equation. E is equal to minus 2.18 times 10 to the negative 18 joules times 1 over n squared. That's the same as Bohr's equation. And it was obtained exactly in this form by a completely different route. Okay? So if you had a hydrogen atom in an excited state, or you had a hydrogen atom in the ground state, it could absorb a photon of the right energy to promote the electron up to an excited state, and then it could release that proton or that electron to come back down to a lower state, and a photon would be released. It all works just like it did with Bohr. E of the photon would be, and this should be minus delta E of the atom, and here are the delta E of the atom. Here's the delta E of the atom equation. It looks just like Bohr's. Okay. Questions on energy levels? Nothing new to learn there? E of the photon always has to be positive. And if a photon is emitted, that means the atom had to undergo a decrease in its energy. So strictly speaking, E of the photon is equal to minus delta E of the atom. It depends. I would prefer to divide that equation into two parts. The first part is E of the photon equals minus delta E of the atom. The second part starts with delta E of the atom, and that's equal to minus 2.18, so forth and so on. I think that's a safer way to do it than I did it there. Thank you. Okay. You know what? That's the end of Chapter 7.